Hello, this is a Physics MC, and this lesson has two goals. One of them is to be able to describe and explain constructive versus destructive interference, and then another goal is to be able to calculate constructive and destructive interference path difference, and we're going to use that with diffraction gratings and diffraction patterns. So let's start off by just explaining what is constructive interference. So imagine you had a wave propagating through space here, or a medium, or it doesn't matter what it is. So you have a wave going through space, and let's say we had another wave that was slightly longer, but not the wavelength itself, but just let's say that it was slightly longer, or maybe it was traveling the other way. And if you look at this, if you break this down, notice how they line up perfectly after this initial point, after this first initial spot. So that's kind of neat, because when waves line up like this, that means that they're in phase. So that means that this point up here is at its peak. This is at its peak. Those two are both at a peak, so that they could add together to make an even larger wave. So I'll extend these lines here. This is just breaking up those different wavelengths. So those two waves would actually add together to make a larger wave. It would add together to make a larger, steeper wave. In fact, we could add this point, and that point would be the sum of those 2 points would go there. Once again, we get some really steep waves. This would be constructive interference, meaning that those two waves line up perfectly. Now, the opposite of that would be if waves were not lined up. They were out of phase. So let's draw what that would look like. So if waves are out of phase, you could imagine it like where this one's at its peak, this one would be at a minimum. It looks something like that, like that, like that, like that. So maybe these two waves, maybe this one traveled a little bit farther, so it's traveled one part of a wave farther, so now they're not lined up anymore, so that this part would line up with this part, meaning that those two parts would add together and cancel each other out. So you would just get this as a resulting wave. Those waves would just cancel each other out and go right through each other, and they would really annihilate each other. So that they can either add together and basically double their size if they're the same wave. It's constructive interference, or they can completely annihilate each other and they'd be destructive. So there's actually a way to produce interference patterns, and we're going to talk about that next. So let's start with, let's go black here. Let's say that there's waves traveling through two openings here. So we had some waves, maybe let's do that in red. So there's waves on this left side, and they're propagating to the right here. So you got this big wave just going to the right, and it approaches this barrier. And notice that there's one opening right here. There's another opening right here. As this wave enters that opening, it's going to spread out. You can imagine like a bunch of people in a burning building, and there's a door right there. Well, they're going to squeeze through that door as much as they can. And as soon as they leave that door, they're going to spread out as much as possible to try to let more people out and try to get away from the burning building as much as possible. So I'm going to show that the wave is actually propagating outwards by doing this. I'm going to do the same thing with the other opening here, except I'm going to do that in blue. Show, so you can tell that, I mean, it's still the same wave, but I just want to make it more visible that there is two openings here, and show how they interact with each other. So we can imagine that those two waves will keep spraying out for infinity. But let's say that there was a screen here, and we could kind of capture those waves on the screen, like the relative intensities and brightness, and they would say they're light waves, for example. We could imagine them as interfering that way. Oh, it's a bad line. Anyway, so I'm going to notice how they cross at different spots. So let's look at this spot right here. They cross. They cross again here and here and here. This is not lined up at all, but if it was drawn better, you can just imagine a straight line going to here, and they would intersect at that point. Cross, 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 cross. They would interfere here again, and here again, and here again. You can notice how they there's points where they intersect, and those intersection points, if it's drawn really well, they'll keep lining up pretty well, and they'll produce either constructive or destructive interference at these points where they line up. Now, the cool thing is that these points, if everything's drawn to scale, will always be the same distance apart from each other. Some distance apart, maybe you'll call that distance x. Or IB likes to use S for distance, so let's use S. So we call that distance x, or maybe a distance S. That these points from here to here is a distance S away, and this distance is S. From here to here, do that in yellow. From here to here is S. From here to here is S. From there to here is S. From there to there is S. That's the distance S, okay? And, well, let's kind of look at another view of this, of what causes that to interfere, or what, is there a way to calculate it, where on this screen there'll be interference or not? Well, in order for, let's say, look at this part right here. In order for there to be constructive interference, those waves have to perfectly line up. If you look back at the last page, for constructive interference, draw that again. It would be if this would line up with the black one. The green wave and the black wave would constructively interfere. They would add together. Well, what has to happen is, well, if this wave from this opening travels 1, 2, 3, 4, let's go 5 points, 5 wavelengths to get to that point. I mean, it travels 5 wavelengths to get to that point. In order for this part down there, I'll do that in green maybe, in order for here to constructively interfere with this wave, it has to line up, meaning it has, remember, has to either be a wavelength longer or a wavelength shorter. It can't be like a half wavelength longer or half wavelength shorter. So maybe, since this one's traveling farther, maybe instead of 1, 2, 3, 4, 5 wavelengths, maybe it's 1, 2, 3, 4, 5, 6 wavelengths, and then it gets there. You got 1, 2, 3, 4, 5, 6 wavelengths before it gets there. And the red one had 5 wavelengths before it got there. But notice that they both meet up at the same spot, and they would both constructively interfere. So the red one, 1, 2, 3, 4, oh, good enough. The green one would look like this, but it would still line up after that point. It would travel 1 extra wavelength farther to get there, but at that point, it perfectly lines up with the red wave. That's kind of neat. And so the constructive path difference, the constructive path difference is actually equal to an equation. We can figure out what that is. There would be a point down here, we could do the same thing. This wave maybe travels equal distance to this wave. And maybe up here is another point where they have another intensity, relative intensity, where they add together. So this wave maybe travels 2 wavelengths farther than this wave, and then once again they would line up again. 1, 2, 3, 4, 5. And the red one is maybe just like 1, 2, 3. Still lines up, even though there's 2 additional wavelengths farther that it traveled. So I'm going to erase this, and let's go to an equation for this. Is there a way to determine where the bright spots and dark spots would be? Let's say if it's light, or for sound it would be loud sound versus quiet. You can actually do the same thing with sound waves or any type of wave, really, water waves. So where would this bright spot right here be? Let's say this is a bright spot. Well, what are we really looking at? That bright spot's going to happen when this wave is exactly 1 wavelength longer than this wave. So the constructive path difference, I guess, is going to equal a wavelength, meaning that if it's exactly equal to a wavelength long, it'll line up again, meaning that if this is 1 wavelength, the other wave has to be either 1 wavelength ahead, right on, or 1 wavelength behind, or some number n wavelengths off. So if this wave down here travels 1 wavelength farther than this wave right here, then we will put 1 here. That means that the bottom wavelength would travel 1 wavelength farther than the top wave. And what would we get? We would get constructive interference. If the wavelengths traveled equal distance, n would be 0. And once again, we would get constructive interference. There might be a spot right here where they would travel the same distance, and the wavelength would be the same. If maybe up here, maybe this bottom wave traveled 2 wavelengths farther than the top wave, we would get 2 lambda. What would we get? Constructive interference. So if that's constructive interference, then the points in between, we would get destructive interference, meaning that maybe these would be nodes or antinodes, and these would be antinodes, these would be nodes. So the destructive interference, I guess, path difference between those 2 waves are going to be halfway in between those 2 points. Meaning if this is bright, it's going to be dark. Bright, dark. If it's light, for example. So that's going to equal, well, obviously we're dealing with a wavelength again, but now it's going to be n plus 1/2. Let me rewrite that a little bit bigger. So that would be, the path difference would equal, well, n plus 1/2 times lambda. Meaning it's really half of the distance between. So we could say, like, hey, if this bottom wave traveled maybe 1 full wavelength here to this point, and this one traveled 1.5 wavelengths to get to that point, we would have destructive interference. Well, the path difference is n. If it was n, it would just be 1 wavelength and 1 wavelength. They would constructively interfere. But now we're doing 1.5 wavelengths. It's going to destructively interfere. We could do the same thing if this bottom wave traveled 2.5 wavelengths, it would destructively interfere. So the destructive path difference equals n, meaning the number of wavelengths traveled, plus 1/2 times lambda, meaning the wavelengths. Constructive interference is n times lambda. And so you could determine where on this we're going to have destructive or constructive interference. We'll elaborate more on this later, but hopefully this makes sense. So can we describe and explain constructive and destructive interference? I hope so. Can we calculate constructive and destructive interference path difference? Yes, there's that equation right there. Or 2 equations. Constructive would be n times lambda. Destructive would be n plus 1/2 times lambda. All right, that's all. Have a great day.